Hello everybody and welcome to this video in which I talk about our paper Fast and Informative Model Selection using Learning Curve Cross-Validation. This paper is joint work by myself. I'm Felix Mohr, working at the Universidad de La Sabana in Colombia, and Jan van Rijn, who works at the LIAX Institute in Leiden in the Netherlands. This paper has been accepted and published by the TPAMI journal and is now presented at the AUTOML conference in the journal track. So what we do in this paper is that we look at the sequential model selection problem, in which you are presented with a sequence of machine learning pipelines and you want to select the best one. So at each point during this process you have three items available. The first one is the machine learning pipeline L that you are supposed to evaluate next. You know a threshold tau, which is the best performance you have seen so far on any pipeline, and you have a number T of maximum training examples you can use for the purpose. You want to know what's the performance P of this machine learning pipeline L when you train on all the T examples. Typically T is 80 or 90% of the data you have available for the task. And in this case, we are only interested in the exact performance of the pipeline if it is competitive. And in that case, we want to estimate this performance P efficiently. If the pipeline is not competitive, we can just say that it's not competitive and we don't know the exact performance, but it's not relevant. So what you typically could do would to use a cross-validation. So for each pipeline, you just do a 5-fold cross-validation, and in this way you estimate the performance P of the pipeline. However, this approach is potentially really slow. Specifically, if you have a large data set, you might spend a lot of time on evaluating suboptimal pipelines. And to improve this, the idea of learning curve cross-validation is to say, okay, let's build a learning curve of this pipeline step by step. And as soon as we see that an extrapolation, an optimistic extrapolation of the curve suggests that the performance will not be better than tau, then we can reject the pipeline, just say, okay, go to the next candidate. In the contrary, if it seems that it is competitive, we can directly jump then to the full training set size to reduce the time necessary to build up the whole learning curve. So this is the basic idea, and what we claim here is that this learning curve cross-validation obtains the same results like standard cross-validation. So it picks the same optimal or another but also optimal machine learning pipeline while being much faster. And in addition, as a side effect, it produces more knowledge because the output is not just numbers, but for each of the analyzed pipelines also a learning curve which can be used for further analysis. So if we look at the idea of LCCV in a figure, you can think of this as follows. So we have observed, let's say, these blue and orange points here. So the orange curve is the validation curve, and the blue curve is the training curve. And the black line, the black horizontal line, is the threshold tau, which is the best performance of any pipeline we've seen so far. So at one point during the construction of the learning curve, we have observed these concrete points, and now we can decide whether we should stop or continue with the process. In this concrete figure, we can see two reasons why we should stop evaluating the candidate and reject it and proceed to the next one. The first reason is that if we take the last two legs of this learning curve here and we extrapolate it, then we can see that at a sample size of 10,000 points, which for example here could be the maximum training set size, we see that even in the most optimistic case, the orange curve cannot reach the target performance tau. So in this case we could say, okay, this candidate will not be competitive, and we can stop at this point. The other reason for rejecting the candidate at this point is that even the training performance is already worse than the validation performance tau of the best candidate we've seen so far. And since also the training curve is monotonically increasing here, so this would be the error rate, for example, in this case we also know that the candidate can impossibly become competitive. Okay, so for either of the two reasons. Now the question is, why is it legitimate to say that the curve can only continue in this green extrapolation we see here. So I said that this is the most optimistic completion or extrapolation of the learning curve, but why couldn't the improvement be better than that? And that comes from an assumption we make in this type of validation, which is the convexity of learning curves. So what we assume is that this orange curve here is convex, and here we see some example of convex curves. So convexity of curves means that if we have falling curves, that the slope is an increasing function. So the slope is increasing from below to zero across this axis. And if we have this kind of behavior, then linear extrapolation is like the most drastic change possible in the learning curve, and typically it will be much less than that. So here we have some example of non-convex learning curves, which would be problematic to use with LCCV, because we would maybe prune, like in this purple case, we might prune a candidate even though it improves more than we would expect. But we also provide significant empirical evidence that the great majority of learning curves is in fact convex in this sense. So from our viewpoint, the assumption of convex learning curves looks fair. In our experimentation, we looked at the following scenario. We simulated an AUTOML tool that employs a simple random search. So this basically says we took 256 random pipelines which are evaluated on 75 classification data sets, and we used once 80% and once 90% for this maximum number T of training examples that can be used. So this is to say that we compare here against 5-fold cross-validation and here against 10-fold cross-validation. In addition, we have two other baselines. One is to say, okay, after each iteration of the standard cross-validation, we employ statistical tests to reject the hypothesis that the new candidate can be better than the best seen solution we have so far. So this could also potentially be an improvement. And the other one is successive halving, in which we present all the 256 pipelines immediately to the optimizer and then let it halven the population in each iteration. In fact, successive halving is not applicable for the cases where we can use LCV in general, because LCV does not require that we know the whole portfolio of pipelines before, which is the case for successive halving. But still, just for the matter of comparison, we did that here. So in this presentation, I only focus on a very small excerpt. I invite you to look into the paper for more details, but I only look at the 31 most expensive data sets, which means that they had runtimes of at least 6 hours to evaluate all the 256 pipelines sequentially, not in parallel. So among these 31 data sets, we see that the absolute runtimes range for the standard cross-validation between something like 10 hours and 80 hours, with some exceptions here. And that using LCV, we can substantially reduce this. If we concretely look here on the right at the relative runtime, so this is the runtime. This figure shows the runtime of LCCV divided by the runtime of the standard cross-validation. And this is summarized across the different data sets. So then we can see that in the median case, LCV only needs about 40% of the runtime that is needed if one would use 5-fold cross-validation instead. So it's a quite substantial reduction of 60% runtime on average for huge data sets. So if we're talking about runtimes of at least 6 hours, and in this case, having a runtime reduction of 60% is quite substantial. Even in the worst case, we already have an improvement of 10% runtime. In the best case, of 75%. Most of the time, LCCV can hold preserve the quality of the best solution. Unfortunately, it's not always the case, which is reflected here in this plot, and this is a matter of future work. Another question that can be answered with the learning curves is whether the acquisition of more data would make sense. So very briefly, one can say, okay, after having acquired these whole bunch of learning curves in the model selection process, one can create something like an idea of how much additional data could help to improve the classification performance. And in fact, we can see that using these learning curves, one is quite able to predict whether these additional data, here in this case we ask whether doubling the data would help improve the data, the performance by at least some factor better. And we can, even the worst case, predict that with an accuracy of 85%. So it's a quite useful tool to also give these kind of insights into the usefulness of further data acquisition. So to summarize, LCCV is a tool that has two important advantages over standard cross-validation in the context of sequential model selection. First, it's much faster in obtaining the same or at least comparable result compared to cross-validation. So we have significant runtime reductions. I invite you to check the paper. We have much more figures in there, also in the supplementary material. Besides, it constructs these learning curves which are just useful assets as additional knowledge, which can be used to analyze this question of data acquisition, for example. So in fact, we would argue that, at least in the context of model selection, it's absolutely recommendable to simply replace cross-validation by learning curve-based cross-validation as a standard procedure for evaluation. LCCV can still be improved for cases where we do not have a convex learning curve, for example, iteration-wise learning curves of neural networks that may have double descent, for example. And it can also be made even more efficient using less conservative extrapolations, so not linear extrapolations, but slightly less conservative ones, maybe using also models. If you want to try it out, there is a pip package that is installable, and we also have a GitHub page with documentation, and we can also find support for the tool. So thank you very much for your interest.